Good day and welcome once again to a Saturday session of the CNPS where we're discussing some technical matters related to modern physical science. Today is the 20th of December 2025, just one day before the solstice. I believe the solstice is taking place exactly at this time, actually tomorrow, winter solstice. And today, we have an interesting speech. It's a departure from what subjects we've been dealing with in the previous months, which are more concerned with maybe relativity and things like that, cosmology aspects and so on. But today, we have Edo Kaal, who, if I may say so, is a Dutchman with perfect English. I cannot fault him at all. So Edo actually started participating in some of the Sunday sessions we have on cosmology. These are discussion sessions. And I think he might tell you a bit more about this himself. Excuse me. He's coming to it, I think, from maybe things related to the electric universe, the people who are talking about an electric universe and Birkeland currents and all that. But today, Edo is actually talking about the structured atom model. And he has quite an interesting conception of what the physical aspects of the atom should be. This uncuttable thing that has been postulated. So he's developed this, what he calls a structured atom model. And he's discussing its consequences, including what he says is the erroneous neutron mass and confusion around this topic. And he will debate some issues which are preventing the mainstream from accepting concepts such as nuclear electron. So his conception, he'll tell you more about this in a moment, but his conception is actually an electron, you know, not disparate from the nucleus, actually embedded in the nucleus. And he's also, I would say, critiquing the conception of the Copenhagen interpretation of quantum mechanics. Okay, now what I'll do in a moment is I'm just making sure if people are having any questions here. I've posted the green room. We have a number of people in the green room. Delighted to see so far. But I'm going to ask your indulgence. However, it will only be for 1 minute. Right, just check that that's all right. Okay, we're already getting comments in. So my request to you is that just give me just a moment to say something about sort of the reality of running the CNPS. Now, you will remember that we entered on a new departure last year, where in addition to requesting membership fees and so on, which would help to run the society, because David de Hilster, the president, has indicated, and he will in a moment actually, because I'll be playing something very briefly, the expenditure which is necessary to keep the society running. And the bad news is that the fees actually don't cover that. So what we did last year is we embarked upon a sort of an endeavor, what's it called? It's a funding endeavor to try to make up the shortfall. And it was reasonably successful. Now, I don't actually have the exact audited figures in front of me, but I think it didn't quite make the shortfall, but it got pretty close. So what has been decided is to issue a new one for 2026 at the beginning of this year. But I'm not going to play a video, which I think took about 5 minutes last year and interrupted our talk. This only is 1 minute. So if you'll bear with me, I shall just play it now. And then we'll start on today's proceedings.
Hello, everyone. I am David de Hilster, president of the CNPS, and this is our annual fund drive. First, I want to thank all of those who have been paying their annual and monthly memberships through our automatic membership system. It is greatly appreciated. Since 1994, this group has been pioneering support for critical thinkers outside of mainstream science, and we continue to do so through our virtual presence, through our Saturday morning live streams and our website discussions, Since last year, we have cut our expenses down to something reasonable for our current membership. In 2026, we hope to implement the Discourse Discussion Group as our primary discussion software. Our current website system, in my opinion, is not ideal. We hope to change that. To donate, you can go to fund.naturalphilosophy.org and donate whatever amount that works for you. Your contributions are greatly appreciated. Thank you.
So that was rather painless, and I do hope you can assist us in that regard. And if you have any questions to me or to David or anybody else involved in the society, please feel free to pose them. Right. So now we can get down to today's technical business. And just to remind you, as usual, the format I adopt is you'll hear a few introductory comments of mine. Then we'll introduce the speaker, Edo, today. And I'll then give him the floor, actually, because he might like to say a few words about himself and what he's been working on and his experience, because I think many of us don't know him, Edo Kaal. And then he'll have the floor. Now, I have checked. He has perfect audio. We have had some audio problems in previous weeks, and I've been slightly culpable in that regard because I've been using an old machine. But I've managed to delete a lot of apps, and I think the audio is good. Edo's audio seems to be excellent. I've tried it just a few minutes ago, but he doesn't have video. So you've seen what he called a mugshot, but I called it quite a nice photograph on the today's announcement. So we know what he looks like, but we won't have the video today. And it doesn't matter because he'll have a lot of presentations, slides, and so on, which will occupy the complete screen. And then what I'll do is when he does finish speaking, it might be roughly an hour, but it could be a good bit less, it could be a good bit more. You don't have to keep exactly to that, Edo. We'll have a look at any of the questions which are coming in on Facebook and YouTube. And I do remind people that you're endeavoring to communicate with each other. Oh, great to see you. I haven't seen you since last week. And what was the weather like or something? So we'll ignore those. But if you have a specific question for Edo, just put question for Edo, or even question for Edo if you're a bit upset at something I said. So we won't miss it. And we'll deal with those first, actually. And then we'll get down to the green room people. So I see there are a number of people who've logged into our green room. They're mainly regulars, which is great. They're all very welcome, and we'll discuss matters with them, and we'll occupy the 2 hours that way. Okay. So so Edo, you're up now. You're up in audio, and I can actually say good afternoon to you. People think I'm a bit affected. I always say good day because it's afternoon here, and most of our participants are in North America, so it's good morning to them. So I said good day, but I can say good afternoon to you. I think. Are you in Holland?
Yes, sir, and thank you for those kind words. And it is indeed the afternoon here, although it is winter time, close to the solstice, and it's almost getting dark already. So
you're even 1 hour ahead of us.
Yeah.
It's just after 3 p.m. It's 4 p.m. there, Western European time.
Right.
Very good. Well, so I think I've said enough, and if anything has not been quite precise, you can correct it now, because what I'm going to do is I'm going to bring myself down, which means that I'm mute, you won't hear anything. But if you have any problem, just say, Ian, come back again. And we've already done a rehearsal. So what I'll do, it's up to you, Edo. I shan't put your slides up yet, but when I've given you a moment to introduce yourself, if you just say, Ian, put up the slides, please, I'll do that. And you should have complete control. You'll be able to advance them yourselves. But if there's any problem, just ask for me to come back. Otherwise, I'll be in the background.
Yes. I'll do the introduction, but I think it's okay if you put up the slides already, and I'll talk around that.
Okay, they're up now. Fine.
Okay.
So I'm going to go now, and it's all yours, Edo.
Okay, I hope this is visible correctly for everybody to see. It should say just full screen, the explanatory power of the structured atom model, which is in a nutshell what I will be talking to you guys about today. And I want to thank Ian for this opportunity to do that. As Ian already mentioned, this is not cosmology or relativity, etc. It is nuclear physics, if you will. However, I believe that the nuclear physics and anything like cosmology, stars, how they function, or the nucleosynthesis, etc., perhaps even the Big Bang concepts, they tie into the nuclear physics, and I think it's extremely important to understand what we're dealing with. So my name is Edo Kaal. I have an environmental chemistry background. That is my original education. Working in that arena didn't really work out for me. Let's say I was already a little bit dissident-like. I worked in the IT sector for a bunch of years, and then through changes in life, I started to do my own thinking, critical thinking, I would argue, or healthy thinking, even one might say. Healthy thinking in the sense that you don't adopt all kinds of concepts that are at the very least disputable, because it will contaminate your thinking. You already know the answer, if you will. So when I did away with all that and started to, as a thought experiment, if you will, do away with all the concepts and start again, figure out what is, between brackets, real, truthful, and what not. And so when I started with that, in the end, after many years, much progression, very slowly at first, lots of studying, I started to see a correlation between what I did and the periodic table. And that became the structured atom model. Now, before I start with the actual presentation, which is a presentation I gave a few years ago, not that long ago, which I use as a basis for today. But as said, I do want to make a cosmology connection. So later on, I want to show another, a little sketch I made. And if there's enough time, the actual three-dimensional builder, so we can take a look at the structure of the nuclei. So let's start with the presentation. The explanatory power of the structured atom model, as said, it is a presentation for another audience in the cold fusion arena, but I think it's very applicable today. So we're going to try and do that. I'm going to have some few assumptions and basic rules to talk about, or let's start with that first. When we imagine a dot that is a point-like particle, there are no dimensions, as in volume, as in, actual ranges, or a hard shell, or not even a hard shell, and a sphere of influences, whatever. However, a point particle has no dimensions, meaning I could stack, a million of them, and I still have no length or breadth or volume. So that's not truthful. So we're touching already the Copenhagen interpretation, because there are no, and everything that relates to it within the quantum mechanics, because there are no point particles. So that was the first assumption, if you will, that I made. Everything has a volume. We live in a three-dimensional volume, world, reality, if you will. And when we look at the nucleus, there are many hints, and that's what I did so much studying. When you look at the sizes that are known, or more or less known, of the nuclei, for example, or one proton, one nucleon, you find out that, that's a stacking of nucleons, meaning there's an actual, structural thing going on. Why is there a structure? Well, if we look at the periodic table, there are patterns there. There are things that occur again. The periodic table, there are periods there and rows there with similar attributes, for example. So that is a clue already that there's not only volume, there's not only an organization or a chaotic organization, there's an actual organization going on. So that's how we go through it. And then later on, we looked at the physics concept. Oh, let me say this first. So what I deduced is the structure of the nucleus without going into what you could say quantum mechanics. What I mean by that is forces or charges or concepts like a strong force has to be there, or a proton and a neutron are made up of quarks, or etc., etc. These are concepts that put you in a certain direction, if you will, in a way, you're working towards the answer. We think we know, however, we don't, because we really don't understand it. And then, so I want to go through this presentation and then later on come back to this, what I just told you guys right now. Oh, guys, I should say everybody, of course, just before. In the structured atom model, the neutron is no longer, and I want to emphasize that, a fundamental particle. There is still a thing that we call the free neutron. I'm not trying to fight the mainstream like, this does not exist, this exists, etc. In my view, from the structured atom model point of view, there's only one particle that is what we call the nucleon or a proton. You could also all call them neutrons. That doesn't really matter. We'll get back to that later on, and I hope it will be food for discussion. Instead, we see it as a combination within the nucleus. So the nucleus would be simply constructed of protons and electrons. The protons being the one real particle, mass-wise, if you will, and the electron, well, that's a facilitator more, if you will, we found out. The protons, by these collective attracting forces, so if you will, the raw Coulomb forces, if we strictly look at that, plus and minus charges, if you will, and we put an electron in between two protons, then we get a system that is absolutely stable, at least forces-wise, meaning the attracting forces are double of the repelling forces. So two protons would repel each other, we learn. We can calculate those forces. And the electron being in between, whether it's a cloudy donut form or a super small point particle or a complete sphere of influences around it, we don't know. But it's in between, so if you treat them as a point particle again, which is of course a no-no, but if you do that and we calculate it, that system is fully viable. If we look at, I'm not going into many details there. Later on, as Ian said, there's much room, I can show details, etc. For now, I would skip the details. There are many presentations out there that show more detail, and I'm more than willing to talk to anybody about that. But if we look at the rules, we see on the left side the first element, if we will, of course, helium, one sphere, and then the two spheres, which is still helium, hydrogen, of course, excuse me, hydrogen 1, of course, and the hydrogen 2, the deuteron, which in my book is the first real element, the hydrogen 2, because in the terminology of mainstream, it says there's a neutron there. In my point of view, that's the first time we see an electron within the nucleus. So that's the hydrogen base isotope should actually be hydrogen 2 in my point of view. But we see a progression there, and the progression, and we've added some colors for recognizability. That is all. There is no value for, and colors do not have value. It's just to recognize. And you get geometrical patterns. These geometrical forms are created by these collectively attracting and repelling forces. So what we stumbled upon, and this is truthful in a modeling situation as well, and I believe it's reality as well, these things automatically organize themselves. So meaning if you have 12 particles, positive particles, and you're trying to create the blue one on the right, which is the icosahedron or a carbon, with 6 negative charges in between, which are not depicted here, which are the inner electrons, that system will organize itself. We've created a very simple piece of software that I can't show now, but it's there. And you can see the self-organizing principle. So nature is self-organizing on this level. These patterns are recurring in the whole periodic table. There's a backbone. Well, we coined it the backbone because the nucleus is somewhat elongated. It's more organic in form, if you will. It is, in fact, a collection of the repeating forms. In this case, the carbon, which is blue here, but white here. I do apologize for that. And that white is basically integrated carbons within each other, meaning there's one proton that is overlapping in both carbons. If you put two carbons together, one proton is part of both icosahedrons. So it's a sharing function. Therefore, you get 12 plus 11, not 12 plus 12. Pillars of observation, we called it. That is how we deduced the whole structure, if you will. So the proton neutron ratio, at least in classical terms. That was a very important one. We see the progression of the elements on average to the next element by adding one proton and one neutron. In my book, one deuteron system, meaning proton, electron, proton system. Every time you add one, you also add one outer electron. So those two are causally correlated. And that is, of course, the chemical definition of an element, the number of outer electrons. But that is dictated by the nuclear organization and structure. Nuclear reactions are a good one. Isotopes and stability, valence and oxidation states. It's all explained through this structure, if you will. And observations are, of course, leading. This is an animation that does not work. I will show it later if we come back and do not forget it. This is the periodic table, and the animation showed the progression of the elements through the periodic table. So we can later on show that, where you see the nucleus grow. So elements are usually based on the previous element. You add a deuteron system, proton, neutron, and you get the next element. And this is the whole periodic table. We went further than that. When you look at all these structures, there's room for certain structures in between that do not violate all these rules of organization of the structure. Meaning, there is a potential room for discovery of elements in between throughout the periodic table. So somewhere around scandium and calcium in between, there should be an unstable element. However, that element is also isomeric. I hope I said that right, because it will contain the same amount of protons, electrons. So chemically distinguishing might not even work. So how we can do that I don't know. All I'm saying is potentially there's room to find elements that are not known yet. Most would probably be unstable. We're showing it here with the green. Those would be the locations, if you will, where there's a potential for another element existing, but with the same number of proton electrons, if you will. Then we went on throughout the years when we had all that beautiful structure, when we did all that, and we presented that, and we presented it in the electric universe community, we presented it in the cold fusion community, and they were talking all about binding energy, and of course quantum mechanic principles, and how they came up with all kinds of conceptual models to do it. However, it never really worked yet, so no Nobel Prizes. And I went like, I have a structure. So I told myself, I have to challenge myself here. Let's see if we can actually do this. And we tried it. And we used a very simplistic approach, because this whole approach is very simplistic. Simplistic in nature at the very least, right? Not all the colorful language and the enormous ocean of terms that we have within quantum mechanics. We can go there in detail. That is not a problem. But first we need to understand the basics of what is a nucleus, how it sticks together without filling in that strong force already. I know the answer already. And figuring out what the structure is. There has to be a structure. There are way too many strong clues for that. So what did we do? We took that deuteron system, which is, per element. Every time you have the next element, you add one of these, and sometimes a few extra, but that is detail right now. We know a lot about the deuteron system. We know there is allegedly 2.225 MeV binding energy. We also know, if we do the calculation of the masses of the proton and the neutron and the electron, and we do the calculation of its constituent components, I think is the phrase, and we calculate the mass from unchanged fundamental particles, such as a proton and a neutron, and we measure the mass, then we find, and this is one of the major finds, I think, in nuclear physics, we measure something we call mass defect. And the mass defect for a deuteron is not the same as the binding energy. However, within the mainstream model, I can find them making no distinction between mass defect and binding energy. And there's a reason for that, and I hope we're going to come back to that. There's an error, as Ian already spilled the beans there, I believe the mass of what we call the neutron is faulty, it's erroneous, and there's a logical reason for that. And the reason has to do with that binding energy versus mass defect. So we need to pluck them apart, if you will, take away that confusion, because right now, mainstream scientists can take the mass defect value, 1.45 MeV or so, or the binding energy value, depending on your needs to make the data fit. Did I say that out loud, that part? Skip that part, Ian, please. So we did the calculation of all the elements and whatnot based on the structure, based on this concept, and we started multiplying, simply multiplying, meaning every proton that touches another proton within the structure will have that binding energy of 2.225 MeV. So you calculate all the bonds, if you will, between the protons, you multiply it, and voila, that would be your rough calculation method for upfront calculating the binding energy of any element. There is no atom model to my knowledge, but people can correct me. I don't know everything now that's out there. There is no atomic model that can do that. So we can upfront calculate it. So it's not a precise method yet, but that is the next level that we are definitely working on. And that's taking away the mistake I alluded to a little bit earlier. Before we can do that, otherwise you cannot do the precise calculation. So there's a reason why this is such an elusive thing within nuclear physics, within quantum mechanics. Why does it not work? Why do we always find these, between brackets, odd numbers or mistakes or energy that needs to be carried off by the so-called neutrino? We will find there's no use for that thing at all. We did these calculations. I'm going to go to the next page, and here we have the graph, which is, of course, the average well-known principle graph, the average binding energy of the nuclei, of the elements, yeah? So it should be a well-known graph. The blue one is the actual binding energy, the known one, right? It's observational. And the yellow one, which is linear, it doesn't fall off, is the calculated one. But I already said there's a difference between mass defect and binding energy. So the first thing that comes to mind is, which number are we using here? And what is binding energy and what is mass defect? Let me make it intermittent there. It's not part of the original presentation, but if we understand that an element loses mass when it's created in relation to its constituent components, right? So if we take a simple one, helium-4, you have roughly 4 nucleons, say roughly 4 atomic masses. In reality, when we measure the masses, the helium-4 has a little bit less mass. That mass is gone from the system when it fused, and it emitted from that system, we'll come back to that, in the form of what we say a gamma ray, or light, at least energy that is emitted from the system. So it evacuates, it goes away from the system, and the system, which we call helium-4, is left with less mass. That means holding together a nucleus is based on the principle of a lack or a missing energy component / mass. That is where the ESMC square is very truthful and very real, and I think very applicable, and only there, nowhere else. So we need to keep that into account. So that means the nucleons lose mass, and it even increases as we increase the organization or the number of nucleons. And that is, I think, one of the most important conclusions to take. They never taught me. I don't think they teach anybody else. You can say, why is this so important? Well, I think we'll find out. I hope at least. Making it a little bit more like this, total energy. So the total amount of, so you get a larger value, right? So just the cumulative amount of binding energy. And you can see again that the calculated value is linear, and the measured value, the known value, is not linear. It falls off and it drops off. I believe this difference here We coined it stress energy. Perhaps a better terminology would be unfulfilled densest packing, meaning the system is not as dense packed as it should be. It's not crushed as much as it should be. As I told you guys before, not guys, everybody before, the nucleus is somewhat elongated. It's branching. Between the branches, there's space. The bigger the system becomes, the more space there is. So it's less optimal densely packed. And that is what we see here. And that is why there's room for fission here. It does not mean fission cannot occur there. Of course, you need to apply energy, duh. And it does not mean fusion cannot occur here. That is a misunderstanding as well. We say iron and iron cannot fuse again anymore because you don't have enough energy. It would be endothermic. That is correct. However, an iron and an oxygen works just lovely energy-wise. No problem there. When we did some number checking, so is this even truthful? So you go to the statistics and we show here every element step again. In yellow and blue again, the calculated value, roughly, simplistically, from the model and the actual known official values. And you can see the very strong correlation. It's unavoidable, it's there, because every big step that is in there in observation, the calculus is big and there is big as well. Is it small? And the other one is small as well. But the two have no correlating data. They're not based on each other. So there should not be any correlation, let alone so beautifully, if this were not truthful. It's a bold statement, but there you go. What can it explain more? We can explain, therefore, in a nutshell, how each element is structured, how the isotopes differ from each other, because the isotopes have no more secrets, why there are a limited number of extra neutrons being able to be loaded upon an element. So, just a few neutrons, like iron starts at 54, I believe, and then you get a 56 and a 57 and a 58. Those are the 4 stable iron isotopes. But the 57 in between is not stable, and the 55. The 57 is stable. The 55 is not stable. It will go to manganese. So there have to be reasons and explanations for that. And we find that simply in the structure. The cycle of 8 in the periodic table, where does it come from? Well, it comes from the recurring pattern of the larger structure, the icosahedron of a carbon structure. So oxidation state, the number of outer electrons, as I said, it's the dictated by the nuclear structure, form, and the number of electrons there. So the number of positive spots on that carbon ball that are not complete yet, not fulfilled yet, there's still a room for an extra electron charge to sit there, if you will, to shield that. That is what we call chemical connectivity. So when that is complete, we say it's a noble thing now, a noble element. So it does it on its own. In chemistry, we say CO2, the whole system CO2, like covering each other's back. Now the whole nucleus of each nucleus in the O and the C are covering each other, and the whole CO2 system is completely neutralized. It's like an electron shield around it. That's the nobility, or rather in chemistry terms, non-chemically reactive. Alpha decay, I think we're going to go back to that. Double beta decay can even be explained. That is like basically skipping that unknown element there. How uranium can split asymmetrically. So let's go there. The way the backbone of the nucleus grows, it creates a structure, and there's a growth limit. Because the nucleus starts to fall in on itself, collapse in on itself. And in the center there, it's not three-dimensional here, of course, in the picture. But these are like these branches sticking out a little bit in the center towards us, if you will. There are 2 of those as well, and they come too close, meaning they start to connect. When they connect, the left and the right side connect on that spot over there in the uranium-plutonium range. and then at the base they break off and they form two new different nuclei, which are the fission products. And of course, in the collective structure of those nuclei, the binding energy is more favorable, meaning you get a lower ground state, meaning you emit a lot of energy, which is of course represented by the stronger binding energy. And we already knew that because the binding energy is an absence of energy. So that's why I call it unfulfilled densest packing, that between those two lines in the graph that we showed before is the energy that can still be released, in theory at least. Beta decay. So fluorine 18 beta decay to oxygen 18. There's one direct path. This is a known, this is right. This, you can find this stuff on Wikipedia and any kind of official outlet. This is has to do with the gamma rays and the isotopes and the beta decays and the amount of energy, and there are two paths there. So there's two ways it can do that. If we look at the structure, there are simply only two options for a structure, unless you start doing really weird things. But you take it out on the outside where the growth is progressing, you go backwards, if you will. You take away one, you get these decay steps. You can have a direct path, but if you start with a different configuration, which the left and the right side here are showing, so fluorine 18B and 18A, I don't know how I swapped that. You have a, just for color, it's just for recognizing, brownish one and a yellow one. Those are the ones that we're dealing with here. And you can have a starting position where they are still on the right side. So you take away one on the left, and here on the left side, you took away one on the right. Depending on that starting situation, you get your direct or your indirect path. That's what I just said pretty much. Another example, multiple paths, 3 pathways. There are 3 options in my mind. So we can deal within the structure. We can see that the structure atom model really neatly would lend itself, I would argue, for educational purposes to not that this stuff is not understandable. You know, I got taught myself a whole bunch of these things, which I forgot mostly in life again. But what I'm saying is it would be very useful to have a simplistic 3-dimensional actual model, but we have to break with the Copenhagen interpretation for starters. When we can show these things, it would be, you know, you get a mental construct. It would be so much better for students. Let me think there. So these are the direct and the indirect paths. It's every time what you see, it's the creation / destruction of those deuteron pairs that I keep talking about, 2 protons with an electron in between. That is the basic building block. That's your brick in the wall, if you will. So the beta decay process has to do exactly with that, creating or destroying one, beta plus or beta minus. Again, a very simplistic concept, but it works beautifully before we go into much more horrible detail in quantum mechanical terms. If in this, like I said, this is a presentation for the cold fusion community. If you do these fusion steps and you add smaller stuff to a nucleus, it can fail, it can fission. So we can see stable elements. Go back there. You can actually see stable elements like a titanium or a palladium that we see a lot in the cold fusion field. They can fission. Here we have the fission example of applied with the structured atom model. So uranium's the central collision point, if you will. So add slow neutron there, so the neutron can take place there. Those two, which we try to show on the right side, top right side with the yellowish here, that those 2 points come together. As a result, the base breaks off because the combination of those 2 is favorable binding energy-wise. Hence, that's the direction nature always goes, to the lower ground state. The lower part is the remainder part, which is the heavy fusion part. The right side is the lighter fusion part, right? And then we see often decay steps, like the beta decay steps, which causes all the nasty radiation after a nuclear detonation or a nuclear power plant. These are the troublesome things. So if we look at the fission products, no nuclear model works decently or can explain decently. I've learned through Norman Cook, who wrote a whole book about it, atomic models, nuclear atomic models or atomic nuclei. And he explained there is no nuclear model, 30 plus of them, that explains or deals with this topic decently, because we would expect an average normal distribution of chance-wise, whereby there would be a 50-50 split of the nucleus at the very least. Instead, we see there 0. There is no even split of the uranium-plutonium range nucleus. Instead, we really see a very distinct range of a lighter and a heavier product. And that is, of course, a very strong clue. There must be a structure. On the right side, we see the heavier component on the top and the lighter component on the bottom, and then the progression, so several elements, radioactive nuclei, and then you get, uranium's a little bit different than plutonium's different than americium, etc., which are pointed out here, those elements. And you see that it is the lighter element range, meaning the outer branches, that of course have the progression of growth if you load it up, have the more heavier, or they grow in mass, so in extra nucleons, not the break central part. So the central part, which is hiding in the center, that stays more or less the same, which is logic, of course, right? The growth happens on the outside. So everything is congruent, I think is the term. I hope I said that correctly. So this is basically what we can explain through the whole fission process there. I think it's beautifully, elegantly simplistic. No model is truthful, as we always say, but some are useful. And I just hope this might be useful someday. Transmutations, I do believe they are happening in the cold fusion field very much. I think the cold fusion actually stumbled on a mechanism, whatever that exactly may be, that's debatable, of fissioning stable, heavy elements, so lead, etc. The energy in the field, I believe, comes from the transmutation. That is a big debate going on there. I think they're starting to understand that is indeed the case. However, they are restricting themselves to deuteron fusion, creating helium, so an offshoot of hot fusion, if you will. This is all specific for that field. What we think is needed to do that, an ionized plasma field environment, whereby you give the nuclei the chance to fuse/fission. If you do high electric discharges, things seem to fission. If you do it more nimble, things seem to be able to fuse together. There's a lot to learn there in my book. These are just examples of that. More examples of that. So I'm going to skip those two. It's not applicable here today. We think SAM is a really good model, at least for a base of a lemma, and much more today. I believe SAM is a useful model, if only to make a mental construct for students to talk a little bit more easy about it and not get swamped by the details. So we forget, right? We don't see the forest no more because of the trees. That is an issue, I think. Let me go to the end of it, and then I will bring up a slide, and then I think I'm pretty much done. In the future, we hope that, we can do some more experiments with this. I would consider this to be a beautiful example for students at a university. I would, if I think back in my days, I would have loved it to do experiments there on an exciting new field where we just might see transmutations going on and not using, particle accelerators, etc., or nuclear devices and where we find that we might actually be able to do that, try to be the alchemist, if you will. I believe the future is bright in many ways. I think The standard model has so many issues, and I think it's crumbling. I can see many cracks everywhere, but most people feel very alone, and it's time we change that somehow. So this is in a nutshell how I try to give everybody here at least a sense of what the structured atom model is about, how you can use it and apply it, at least on a theoretical part, by looking at nuclear physics. But, and this is where I want to skip the presentation and go to the next slide, there's a connection to cosmology and other things as well. And I have a slide. Oh, this is the builder. Let me show the builder there first. Sorry for the interruption in that way. So we have a builder here, and everybody can go here. It's structuredatom.org, where you can look and browse through the elements, and you can see the progression. The lighter ones, I added the nuclei electrons. Later on, not anymore. It's a repetition. We hope to have an automatic creator builder in the future. It's a redo of it, if you will, whereby we can also add an automatic calculator animator for a fusion and fission principles, and the binding energy mass defects automatic calculations. So no fudging allowed. So this is what I wanted to show. On the left side, we have some buttons, and there's, data there that is all retrieved from the official data, from the most official institutes that we can think of that guard that data. The only data that is not in that sense official is my own data, and then you will see things like binding energy SAM lines. So that is the calculus that I talked about, the binding energy, for example. Going to the slide, which I buried here, of course, now. And that is this. This is the new part, if you will, and this is the erroneous mass. Before we do quantum mechanics and look at strong forces, quarks, gluons, muons, mesons, imaginary particles, antimatters, neutrinos, etc., before we come up with these concepts that were usually postulated in order to do away with a certain problem, such as a problem of my spin doesn't add up on both sides of my equation. Let's add a factor. It's also called fudging. And then we, in 1932, I think it was Chadwick, I hope I say that right, he came up with a collision of an alpha particle, and I think it was a boron or something, and then you created a carbon and an alpha particle and a neutron, something akin. And he determined the neutron mass, which was less than the mass of the proton. And in his paper, he explains why that is logical. So the neutron mass, he concluded, was less than the proton. Nowadays, the neutron mass, there's only one neutron mass in the standard mainstream physics, at least that I can see, but anybody can dispute me there. And that is a fixed value, and the mass of the neutron is more than the proton. How do we know? Later on, in 1933, other people got involved. We looked at the disintegration of the deuteron system, that same deuteron system that I keep talking about. And then somehow, some way, by doing some mathematics instead of physics, and understanding that I changed a nucleon from a proton to a neutron, for example. And so I do not have the same particle on the left and the right side of my equation. And my equation being, two hydrogen bonds in going into a deuteron system, or a deuteron system, which is on the top of my triangle here, to the right side becoming a neutron and a hydrogen one. And you can do that by shooting a gamma ray on the deuteron with 2.225 MeV at the very least gamma ray. So when they looked at it and forgot that convenient thing that that there's a change of the nucleon there, in this case being the neutron, because the neutron came from a nuclear system, the deuteron, and it became on its own system, on its own, released from the nucleus. And why was it released from the nucleus? Well, we shot a gamma ray at the deuteron. We gave back that energy, we gave back that mass. But when those protons, I call them both protons, and I use the terms here interchangeably, and I apologize if it's confusing. When they get back their original mass that they lost when I fused it, now they must make distance again, because that is the original state. I put them together from two loose hydrogen ones, and I made a deuteron. I shoot a gamma ray at it, and if I do that in that range, I get a neutron first. That's what we call the free neutron. But it's not the end of the story. The neutron still decays automatically with the big arrow to a hydrogen 1. You can argue it's a proton and a loose electron. That depends a little bit, but it's a hydrogen 1 again. Proton, electron. But we add, and that's a known observational thing, 0.782 MeV. That is therefore attributed to that neutron. And that is a free neutron. And that needs to be distinguished from the neutron within the nucleus. That is all we need to do. This neutron, free neutron, is indeed a fixed value. And it is indeed that system. And what is it? It is an intermediate state of a disintegration process that is not complete yet, because it's still disintegrating. Half-life 10 to 15 minutes. This number here, the 0.782 MeV, is attributed to the neutron. Not only that, it's the free neutron. And that free neutron value, fixed value, is put back into our calculations of the masses, the constituent components, calculations of the masses. So we attribute a fixed value to the neutron. But it cannot be true. The proton was fixed, the electron we forget for the convenience here. It's just negligible right now. And then the neutron, but the neutron is more than the proton. So the deuteron should weigh more, should have more mass than the constituent components, because there's a neutron there now, right? The proton changed into a neutron. The proton plus an electron plus 0.782 becomes a neutron. That free neutron fixed number is applied to the nucleus. So you should have a more massive deuteron, a more massive helium-4. The graph I showed should go up instead of down. This is a problem. Mainstream is completely, and this is a bold statement, and we can argue and everybody can shoot me as a firing squad. This is my statement. This is simply wrong in the mainstream. The neutron, which we call the neutron, I believe there is no neutron because it's a combination. The neutron within the mainstream uses that fixed value, but it's not true. Because if we go back to the presentation and we look at the graph, let me see if I can do that still. We have the graph there. We can see that the average binding energy varies per element. And that means the average binding energy, the average mass defect, the average lost mass and energy per nucleon, and the proton is fixed, so that one didn't change. So the neutron must have changed within the nucleus. And not only that, it must have lost mass. So the neutron within the mainstream conceptual model should be a variable, and it should be less than the proton. The proton is the original state. We know that because the neutron is a fixed value, observational, and it goes back to a proton, observational, fixed, stable. And this is where the magic happens and something changes. That is where ESMC happens. The only thing I can agree with Mr. Einstein so far, I think, but I'm not an expert on that at all. But I do believe that the proton-proton fusion is cosmology and proposed as functioning of stars. I do believe that the energies that we're talking about with this, and they are wrong because the carbon, let me say that still, the carbon-14 and the tritium decay, hydrogen-free decay to helium-free, and the carbon-14 to nitrogen-14 are going upwards in the ground state. So they get less binding energy. That is not in the right direction. Nature doesn't do that. Nature doesn't flow up a waterfall. Water doesn't flow upwards in the waterfall in the other direction. It's a comparison simplistic model for the nuclear decay step. It always goes downward. That is because that number here that is attributed to the neutron and then applied to the nucleus. So that's the problem here. And once we start understanding this, just by looking at the level of the nucleons, no other things yet, we start to see that we need to understand that the nucleus is held together by the absence of energy that is emitted during a fusion process. That means there's an electron facilitating a connection between protons. As a result, the protons must shed that energy. That energy is equivalent approximately to the forces that they experience repelling each other. However, as stated, the attracting forces are on average at least stronger, but almost double as strong. And the repelling forces seem to be equivalent to the amount of energy that is emitted. I do not know how that relationship works, but that seems to be the case. This is how fusion fission works. Also, people offer the idea that you can create free neutrons by adding the 0.782 to a proton. I believe that's a very erroneous thing also. So this is a connection that coming from the atomic physics, and I think where quantum mechanics should be working at, which is totally connected to things like cosmology, functioning of stars, neutron star concepts, but also carrying away the remainder mass in the mysterious neutrino, for example, in beta plus decay steps, I think it is. That erroneous carrying away energy suddenly attributed to a neutrino, which normally never interacts with matter, except when we're dealing with this unstable isotope here. The neutrino readily interacts mysteriously, no problem there. And that mistake is there because of this attributed 0.782 number. If you fix the neutron mass and apply at least that, take away that and apply that number to the neutron within the nucleus, and we do our homework again, we calculated the masses, now we can see the correct values, meaning the very enigmatic tritium and carbon-14 decay steps, which is very enigmatic because nobody can really explain them properly, are no longer enigmatic. They are completely logical. They are going downstream, down waterfall, and they are precise. So the whole problem drops off the moment we understand that the neutron mass is A, 0.782 off, B, within the nucleus, not the free neutron, in the nucleus is a variable. And that this is the gig of what we call fusion and fission. And fusion and physics are at the basis, I believe, of, cosmological functions again. But this is where I seek the interaction. So, Ian, I think you should take it away from me now before I start rambling about all kinds of stuff that's not longer relevant. Thank you for your attention.
Well, I'm happy to come back, but we would have been delighted to hear you go on for a little more time. You've kept exactly to the hour, actually. Oh. A little less because I rambled on for 5 minutes at the beginning, but it's just 1600 hours for me now. So thank you very much, Edo. Shall I take down your slide maybe now?
So sorry, what was that?
Yeah, okay.
Yeah, take away the slides, please, and do that.
Right.
Okay.
Well, maybe I just start the ball rolling by just imposing upon you one or two comments or questions, and then we'll get to the questions. Actually, we don't. I think we only have one question, which I will come to, or one comment from the social media people. I think this is something that maybe a lot of people coming to our conferences through the Facebook and YouTube are not, I won't say not interested in, but it's a bit beyond them. They study a bit more things at the macroscopic level. We even noticed the same where we have something maybe related to quantum theory. But I take it that we'll be able to absorb the next 55 minutes or so by inviting people from the green room to come in. But before doing that, if I may just say, yes, well, thank you very, very much indeed. I found it stimulating. And actually, I have heard you before talk on this subject at the cosmology sessions. And what we've been doing recently, by the way, ladies and gentlemen, is we have had speakers speak both at these Saturday conferences with the very standard form. We allow the speaker uninterrupted presentation for an hour, and then we grill him. But also the Sunday sessions are a bit more informal. They take place over Zoom, and we can sort of interrupt people and so on and so forth. So there's a different format, and I think the speaker can engage in concentrating on different aspects, not only because of the different format, but also because of the different audience. We have a wide audience now of people, although today I'm not sure if we have so many, but who are not regular participants in the CNPS technical sessions. But I found it very, very useful, having listened to Edo's earlier presentation to the cosmology session. I was delighted, actually, by the way, if I may say so, early on, that he warned us about early bias. Be very, very careful about that. It's the old Sherlock Holmes dictum: do not theorize before you have sufficient data, because it tends to bias the mind. You then, if you form your theory too early, you get data later and you try to twist it to. Yeah. You know exactly what I'm talking about. Twisted to accord with your preconceived ideas. Okay. I also, found it interesting. I mean, you talked about the fudging of new particles and so on. This is something which is dear to my heart as well. And it appears. Well, here's maybe a question. It appears your ideas of the electron glue, or whatever you called it. So that's basically, is that, doing away with the conventional view of quarks as establishing the strong force?
Yes. I think what we in the mainstream is conceived as quarks, I think is reflected actually as the structure, meaning if you see 3 quarks on average, that is because on average within the structure that I talk about, you see 1 proton touching 3 other protons. So I made a comment to a nuclear physicist that I know and sometimes communicate with in Belarus, in Minsk. And he was about to finish his PhD on the topic of quarks and all that stuff. And he never finished it because at the very last he ran into, let's say, awareness that what he was doing was not proper at all. So he would be very welcome in this group here, because the quarks, I mentioned to him, I said, well, unfortunately, there are only 3 quarks because my structure shows also 4 and 5 connections as a possibility. And he says, well, it'll be fun for you to know that the mainstream, now these are his words, I don't know, that the mainstream does know something as a tetraquark and a pentaquark, I think is the terminology. So the structure does reflect the quark field, but the quarks are not smaller particles making up a proton. They reflect the structure actually. And the strong force, to connect that one immediately there, I feel that question coming up. The size or the influence sphere of the strong force is allegedly approximately, what was it? Let me think, 6 femtometers or so, 2 times an electron radius or so, which is exactly that range of an electron influence. So the nuclear electron range, if you will, the size of what we conceive of the electron, because I don't know what an electron is, and the strong force a range of effect, I'm not sure how they coined that phrase, is also coinciding. So I believe the structure is very much reflecting things that we talk about within the mainstream. But the mainstream, I think, makes some conceptual, in hindsight, we can say errors, or in respect, in comparison to me, there would be errors. I don't like the term errors here, but there are conceptual things that were useful at one point, and there are definitely those relationships there. I don't think there are smaller particles, etc., however, whatsoever.
Okay. And by the way, on that, I may say a word about this when we're closing down, but um, we're just looking for further talks. And this gentleman in Minsk, if you'd like to put him in touch with us, if he'd be willing to give a talk in the future, that would be most welcome.
Oh, I would be happy to give him a heads up there for sure.
Excellent, excellent. I've only one more point before maybe getting to the more general response, because don't want to dominate the talk. Yeah, I was interested in obviously your explanation of transmutations and all that, and fission and fusion and so on. So I think I may have adverted to this briefly before at one of our discussions, but am I correct in saying that you would explain the early Rutherford scattering experiments, where you had the positive charged particles deflected, but by saying there's maybe an asymmetry, or there's a concentration. I'm probably saying things wrongly now, but correct me if I'm wrong. A concentration of protons at the periphery of the nucleus, which would scatter those. Is that the way you would explain it?
Let me see if I can do this. So yes, if I go back to the deuteron system that I keep talking and harping on about, I'm sure everybody can remember that one by now. 2 protons and 1 electron in between. So if you purely look at charges, that central area, right, where the 2 protons are touching each other, those 2 halves of those spheres of those 2 protons are negated, if you will, by the electron. So charge-wise, that's 0, right? Negated. That's what you could call the neutron or neutral zone. The outer part, so the sticking on both sides of the halter, if you will, the two protons together, so the outer part, that's where your positive charge still remains, 2 halves, if you will. Now, even no matter how large you go in the elements, you get these sticking out half charges, if you will. And I would argue that is through a Rosetta Stone comparable to what we call the Coulomb barrier, right? The repelling effect of the nuclei. So that is a very, very real thing, only slightly conceptually different, that is all.
Okay, well, that's been very, very useful. Thanks a lot. Now, there's really only one question so far, and I invite anybody else on the Facebook and YouTube to come in with questions before we go to the green room, or even during that time. But it's just a point that this gentleman made, or it could be a lady, magnetocosmos. It's not really a question, but he says that this reminds me of the work of James Carter. Have you anything to say about that? I think he might have been a bit of a rather dismissed person whose ideas were thought to revert to 19th century's ideas of people like Kelvin and so on. But I don't know if there's a similarity there. Are you familiar with that, Edo?
It doesn't ring a bell, maybe not, because there's truthfully so much out there. And as time progresses, I keep running into people that you never heard of, right? But did great thinking, or tried to do it, or came up with a concept, or tried to do the same. The world does seem to have quite a few of those, even though they are quite rare. Help me understand, please, what it is. I don't know. I don't think I know. Maybe I do. I don't know the name.
Okay, well, if Magneto would like to come back on that and talk about what aspects of James Carter's work, was it atomic ideas or things in the ether?
I'll Google it, but I'm so sorry. Yeah. I don't have an answer.
No, that's fine. That is fine. But I noticed that Cornelis made one or two sort of practical comments. So if he wants to put it in the chat, or I think he's joined the green room, so we can ask him later on if he has any questions on that. So now James Keane has actually put a number of comments down, which are, it's useful to have down to see what his thinking is in the private chat. But rather than my Carl Reef has something as well. Yeah, he's asked for some explanations and questions and so on, and said he has data, I think, which actually might back up some of your ideas. So, Jim, could I bring you up and ask you to go through your points, and anything else that has occurred to you in the meantime, put them directly to Edo? Yeah, I've got you up, but funny enough, there's no camera. I don't even know if I have your voice. Can you hear us, Jim? That's odd. Because he's here in the green room, and his mic is not muted.
I
Oh,
think
there he is. There was a delay. There seems to be a delay, Jim. But did you hear what I said?
Hello.
Okay, hello. You have data which would appear to support Edo's model. Is that from your binary mechanics simulation?
Hi. Hey, can you hear me?
You're breaking up. You're breaking up.
If I can make the suggestion, if James turns off his cam, it might help.
Yeah, could you switch off your cam, Jim?
Hello.
No. Switch off your video. I don't think I can do it. Your voice is coming through very poorly. So we're suggesting if you switch off your video, please.
Hello.
Can you hear me? Yeah, see, Edo and everybody, the person has to switch off his camera or mute his mic.
Seems to be
I don't have
frozen.
control of that. So unless Jim tries that, I don't think we can really go ahead. I maybe while Jim is doing that, Jim, I'm removing you for the moment, and I'm suggesting that you switch off your camera. I'll just he's typing something. I don't know. Comments. Maybe we can go through some of the comments before that, because let me see. Oh, has he done it? Let me see now. He's. I think he's gone out. He's going to come back again. But he okay. I've made the first point. He asks Edo, how are these masses measured? I don't know in your.
What was it?
I don't know what detail he wants.
It's originally, what was it again? They measure it in a electric field, I believe. I hope I say it right. I'm not an electric engineer, right? So when I read through these papers, I see what it is, but I often forget detail. Strangely enough, I work a little bit different with information.
Okay,
if I need detail, I go back to it. I think it's the protons and the electrons. They show resistance, movement / resistance in an electric field, if I say it correctly. The neutrons, however, do not, if I'm not mistaken. But
so the mass spectrometer.
Yeah, so the neutron was mass-wise not measurable because of that. But we can do the whole nucleus, and we can do the protons and the electrons, and then you get the story of the constituent components versus a measurement. Now, how they do the exact measurement, I'm so sorry. I think it's through an electric field, but I don't know.
Jim, I see you're back. You logged out and you're back again, but I don't think it's any better. Could you switch off your camera? No, he's frozen. Okay.
It's a poor connection.
Yeah, poor connection. This has only happened in recent weeks because Jim is a regular participant. I had problems about a month ago, and I think I've resolved them by deleting a lot of apps.
That will help, yes.
Yeah, I have a new computer, but I've actually got StreamYard up on it. But unfortunately, with the new system, there's double authentication, which means that whenever I go in, I have to contact David DeHilster in Miami to give me the code, which is they've given. So I didn't bother today. I just went on the old system. Okay, so I'll just go through Jim's comments, but unfortunately, he's not responding. He suggests that your overestimate of binding energy may be due to lack of the geometrical constraint of the BM spot cube lattice. Well, I warrant that we can't deal with that without Jim's explanation, because he's his binary mechanics model is it's something which requires his own description as to why this should be so. So
I think
if
he
you want
may
to,
be coming through now. I see his video.
yeah, yeah, Jim, can you speak a bit?
Oh, hi, Edo.
Hi
Can you
there.
hear me?
We
Yes,
can
sir.
hear you now.
Oh, okay. Ian seems to be hung up, but I have a couple of questions. First, thanks for the great presentation. As you might see in the comments in the private chat, I have some data which appears to support your model.
Okay.
You might want to look at figure 13 in my latest paper, Binary Mechanics Cosmology. It shows a stair-step um, um, pattern of nucleon addition to higher Z atoms, which indicates the kind of structuring which you're talking about, and I think it supports your model. Ian, I still don't see Ian. But if you can hear me, I have
Yeah,
some questions. What is nucleon radius? That's my first question.
That is simply what we know as the proton radius or the proton radius puzzle. The proton radius, of course, is a direct component. It determines R, the radius, right, in your calculation of Coulomb forces. So the proton radius is super casually connected here. If you change the radius of the proton or what you call the nucleon, then that changes as well. But it's simply the size of the proton. That's what I mean by it.
okay.
Well, like in general, it's estimated to be in the vicinity of 1 femtometer.
Yeah, 0.8284 or so femtometers. Yeah, radius, that is.
Right.
Yeah.
Well, older scattering data, that's one way to determine it. And older scattering data shows about a 1.2 femtometer radius. Okay. In other words, when you're showing these spheres in your wonderful illustrations and animations, you actually believe that they're not point particles, the nucleons, but are have a definite finite radius. Correct?
That is correct. In fact, when I said I started out many years ago with my brain thought experiment, I recognized, I recognized something. That's why I said I wanted to start with a clean slate. So do away with all the concept, everything that comes up, ditch it, throw it away, start over, and start at the one particle, if you will. And when you do that, the first conclusion that I drew in the new build-up of things, if you will, was there are no point particles. We live in a three-dimensional actual, well, whatever we call this, reality, whatever that may be, but it's a three-dimensional spacey thing, right? We have coordinate, there's volume, there's length, there's size. Nothing is zero dimension. So my first conclusion is whatever we call a proton or a nucleon or an atom or whatever, it has size. There is no such thing as a point particle. And but it causes some issues in your calculation realm. That's a practical thing. So they don't like it. But that was my personal first conclusion. Yes. And I think it's a very
Okay,
important.
excellent. Thank you. Wonderful. Now, it seems that in several of your illustrations, my friend, your work seems to overestimate the BE, um, and this
Binding
may
energy.
be due to a lack of the geometric constraint of the cubic binary mechanic lattice that I work with. How do you account for the fact that your work seems to be overestimating the BE consistently, it seems.
The overestimation comes from partially because what we call the mass defect, right? That's the mass defect effect. So that's partly where the drop-off in the line of observation comes from if you compare it to the raw calculus. So the binding energy is there. I would argue that the binding energy actually is a linear line, what I calculate. However, when we look at the reality, when we look at the total mass of the nuclei, there's that drop-off, right? One or two particles at the end, one or two proton masses at the end when you reach uranium. And that is the dropping off of the graph of what we know it is. It does not mean the calculus is wrong. It means we're exposing actually exactly why fission works. If the lines were coinciding, there could be no fission, there would be no release of energy. So the difference between the lines is it actually the energy that can be released through the fission process.
I see. Well, perhaps that difference in those lines that you showed in several graphs might be, that is actually something that supports your model. That wasn't clear to me due to the presentation. Now, I guess it all comes down to my second point in the private chat here. How are these masses actually measured? Now, this might be a very elementary question, but a lot of what we're talking about here seems to come down to exactly how these masses are measured and what assumptions are there in those measurements. And, how do we get these masses?
So you may want to repeat yourself a little, Edo, because we did deal with this when Jim was off the line.
Understood. I'll try and summarize. From my understanding, the masses of nuclei are measured, I believe, in an electric field, if I state that correctly, because protons, electrons, and nuclei show, more or less resistance depending on what you put in there in relation to that field. The neutron on its own, I believe, cannot be measured that way, right? I think. But I don't know the details of how they did this. At some point in time, I went there and I read all about it, and it satisfied me, that this is a real thing, a trustworthy observational thing, if you will. So these are real measurements of nuclei, and then they determined the masses. I think that is an actual real thing, and that is proper, if you will. How exactly they do that, I'm sure. If you post a question to an AI search engine, you will get a very elaborate answer, better than I can.
Okay. Good answer. Thank you. Finally, I have here. This is just a simple question. You use the abbreviation LENR. What is LENR in simple terms, please?
Very good question. Most people have heard of the term cold fusion, right?
Yeah.
But cold fusion got a little bit burned, pun intended. The hot fusion field is also there. But then they came up with plenty new terms, condensed matter, nuclear science, for example, but also low energy nuclear reactions, which is more or less becoming the term. Some people still show resistance. In my mind, that is the best terminology, right? Low energy input, nuclear reaction, right? So this is a new novel thing. And of course,
low energy nuclear reaction.
Yes, sir.
Okay. Well, look, perhaps I can communicate with you further by email. Congratulations on your very interesting work, Edo. Again, I think I have some data which supports your model because It's actually in Figure 13 in my latest paper on the binary mechanics website.
I will be happy to come back to that, sir. But I need to do my homework and find that paper and all that stuff first. But let's do that outside.
Understood. I understand. As a matter of fact, I think I've got your email. Now,
Yeah, you
Ian
will have it
seems
from
to
the
be out of
cosmology
the
session.
picture here. So I don't know what's going to happen here, because these are the questions that I had. And I think other people in the green room should be allowed to speak and interact with you, sir. But I don't know what, since Ian is gone, he's the one who brings people up
He's
and
not hearing me.
takes them down.
I-
So I don't know what we can do. We can sit
I
around
can
and
still
chit-chat,
see him.
I guess.
I can still see Ian, but you might not be able to hear him. I don't know. But Ian
I
is
thought you
still
were
there.
ignoring me, but he doesn't hear me.
Oh,
I think
okay. Well,
everybody
I'm
else-
done, Ian, if you
Yeah,
can
I'm
hear
putting
me,
it down
sir.
now. Thank you very much, Jim. We'll
And thanks,
hope-
Edo, for your answers. All of this I need to look into in a lot more detail. Thanks to you.
Thank you again. Thank you again. Okay, I hope everybody else can hear what I'm saying. Now, Dennis Allen is actually got his mic active, but there's no video there. Yeah, okay. Denny, do you have any questions for Edo or any response to what he said about this new model? There's a bit of noise, background noise, Denny. No. Could you maybe try to switch off your video and try speaking? It's very, very poor. It's very, very poor.
That is not audible.
It's not audible. Denny has been having problems. I'm so sorry, Denny. I know you've had problems. He's not even hearing me. We were comparing notes over the last couple of months when I was having problems. They were the same problems. You have a very old system, which I think is working on Windows 7 or something. And I really think StreamYard is struggling. So we're going to have to leave it, Denny. If you want to put any points, I'm sorry about that. It has to be worked out. I'll talk to you off stream about that. If you want to put any questions in the chat, we can do it. Now, I see Jim Morrison has come in, and I think good. At least he's responding, and I think his audio and video are good. So, Jim, I brought you up. Do you have any response to Edo's points? What is your whole conception of this, or do you have any questions, or do you think anything is needs clarification?
Well, maybe I could try to relate it to ether.
Yeah.
I've always thought of the mass defect actually being when a nucleon supposedly has a mass defect, a fusion or whatever. That it's not a magical conversion to energy, quote unquote, although energy is exchanged, but the mass doesn't disappear. It actually transforms into ether particles.
Well,
You heard of
the
that
main what is understood here, and I don't try to argue here, but what is understood here is that part of the mass, whatever that may be, right? And it may be energy already when it's part of the proton. So what I'm stating is the mass that is emitted from the system in the form of energy, in the form of a gamma ray, for example, actually is sourced by the proton. And what we call the neutron is therefore a variable within the nucleus, as I tried to explain. So the proton is the source for the energy emitted. And when that, as long as that energy is gone, the system sticks together. So there's a whole something going on there. At least that's my understanding, the way I see it. How it relates to ether, ether is a very, very deep rabbit hole, if you will, or a can of worms. Absolutely, I'm not unfamiliar with
can of worms.
Well, I have a simple conclusion. Years ago, I did go to ether for a while. Very interesting topic, and it's fascinating to think and talk about. But in the end, I concluded that, and I don't mean to insult people here. This is my own personal conclusion for me. In the end, I kind of concluded this is a useless thing. There's not enough tangibility, if you will, right, to do something with it. It's all so vague. And I concluded through my atomic research, actually, that the ether is actually nothing. And I mean that in the literal sense. And I state that because we need an isolator in this realm, in this reality. An isolator meaning if the protons and the electrons, if we stick to this level of understanding for just a second, there as particles, if they were to always be able to interact via an ether or have a direct connection or whatever, the universe would not function at all. Energy would be leveled out immediately, for example. There would be no capacity function, and that sounds very electric engineering, but biological functions, biochemistry, nothing would work no more properly. So the ether in my mind, and that's maybe a cop-out to the whole topic, and I'm very open to other explanations there for sure. But I concluded it is actually nothing, because that is the best isolator. That is actually what we need in order to have the universe working. But people are allowed to disagree there very much. It's philosophical for me.
But by the way, another of these the panoply of names, you did ask Jim whether Edo was the author of Structured Model discussed by Gareth Samuels. Have you heard of him?
You're asking me, Ian?
Yeah. He was asking
Yes.
you, Edo. Is that you collaborated with him? Did you?
Well, Gareth Samuel is another interesting phenomenon. He's what we know these days as a YouTuber, right?
Okay.
He's a YouTuber in science, so he is in a way competing, but in a good sense, with the Thunderbolts project. That's how he started out with the electric universe and stuff. And he broadened his horizon, and he talks a whole lot about cosmology, and actually he would fit right in here in my mind as well. So he makes these exclusive, wonderful put together videos about usually mostly cosmological topics. But yes, he has on occasion made some videos about the structured atom model as well. He kind of likes it, I think. And so we do communicate. Yes, very much.
Okay. Well, so anything else, Jim, that you want to put to Edo?
The diagrams you showed, the fitting together of the nucleons, do they effectively get closer when they fuse, and the space or the volume that might be between them, they kind of move into, they kind of overlap, they penetrate each other somewhat.
Right. No. Well, the short answer would be no. In principle, that's my assumption, if you will, right? You have to start somewhere. I assume that all the protons are the same, right? There's no difference between one and the other. That's one. Except for what I explained in the variability there. But it's, the whole collective within the nucleus, they're still all the same. Structurally speaking, therefore, there is no change in that sense. So a carbon atom is a carbon atom, and it doesn't swell up or shrink a little bit, something akin.
No, I meant more in terms of...
It's not impossible. If the protons do lose a bit of mass and energy, potentially the proton radius could be affected there a little bit. And that is
I don't mean the overall radius. I meant the section where they bind, essentially.
Yeah. Well, so the distance doesn't change in my model at all. But
So the
What?
distance between the atoms or the nucleons is equal to 2r.
yes, yeah, it's always 2r, always 2r. However, r might, and this is a big might, I don't know. It's a research question, as I call them. So the proton radius is always fixed normally, but if they do lose a bit of mass, could they lose a little bit of their radius, right? When they fuse together. That is a question I have. It's a simple research question.
And would it be
And I do
equal
not
to the
have
mass? And would it be equal to the mass defect, perhaps?
exact. Yes, yes, yes. So it's a little bit, but might be measurable and it might be truthful. But I don't know what a proton is, no more than anybody else, right?
Okay. And how do you, in your structured atom model, how do you determine the angle between the nucleons?
Organization is a self-establishing system. It's self-organizing. Its densest packing is the best term to do our conceptual mind
Well,
projection.
the diagrams you showed don't
well,
necessarily indicate closest packing.
It's
To me.
It's densest packing. So if I take 4 nucleons, 4 particles, 4 protons, and I put them in a line, you would have hydrogen 4. If I put them in a flat thing, we have something that's unknown, doesn't exist. And if we put them in a tetrahedron, we have a helium 4. The helium 4 is the most dense packed of the 3 configurations that I pointed out. Yeah. So in a line with 3, you have hydrogen 3. If you put it in a triangular with 3, you get helium 3. Helium 3 is more densely packed. Helium 3 has a better binding energy, except in the mainstream. That's why it's so enigmatic. But that's because of the error I pointed out.
Well, wouldn't say that the U-235, wouldn't that be densest packed if it were a sphere?
Yes, but the sphere, it would like to do that forces-wise, if you will. But in actuality, it is still based on the previous structure, which keeps itself intact. So we can't make a skyscraper by putting a whole bunch of bricks together and build a skyscraper in one go. We can make one layer of bricks and then another layer on bricks on top of that. So that's how we can work. You have to have the intermediate stages, if you will. So uranium cannot be built in one go from the correct amount of protons and electrons, and then now I can build uranium. That doesn't work. It has to be a helium-4 first, then a carbon, and then some number of steps in between. And the structure is elongated, and the structure is fighting what you just pointed out. It would like to be that densest sphere as possible, but then you get no structure. Now it's a chaotic system, and it will find structure self-organizing again in the smaller parts. So even if you were to fracture a uranium completely and utterly in one go into all the protons and electrons, you would likely see stuff coming out like an oxygen and a carbon and a helium. I hope this answers your question.
All right. Well, anything else before we leave that particular issue, Jim?
I'm good.
Okay, thank you very much for your contributions. Most interesting. Thank you. Edo, a question has come in a bit prolix from Green Science. We'll just see what it says. Does Edo have an explanation for the de Broglie relation as applied to photon emission and capture and mass deficit in atoms? Could the momentum be delta P equals F, delta T H bar K equals delta MC, rather than just P equals H bar K?
I'm afraid I need a little bit more time to digest this entirely properly. Can I give me a sec there?
Well, I thought you meant you'd like to take it away and maybe come back to.
Well, here's the thing. What is fascinating, and I'm not sure if I'm answering the question, but I'll give it a short go. what I see between the relationship between the structure and the R, the actual distances, for example, the energy amounts, etc. Now, of course, famous people made a connection between frequency, energy level of what we call the light spectrum, etc., right? The photon emission. And I think we can do it in the end, but it requires work still. We're trying to do that. I think we can tie the structure to the actual spectrum of the emission lines and absorption and emission lines, including in the gamma ray spectrum. So I think, but we also need to map and project three-dimensional, if you will, the outer electron realm before we can go to a proper connection and calculation and tying into a photon emission. So I guess it's a promise for the future that we can make a proper relationship in those things.
Okay, thank you very much. But by the way, the same person just made a comment about measuring mass, I suppose. Magnetic
field. I'm so sorry. I said electric. See, I keep confusing.
Oh, okay. I thought you just said it's another way. You agree with this? Magnetic field experiments give the mass.
Yeah.
David Hilster's father did a video on it for the electron.
It's a well-known topic. I just don't have the details at the ready here.
It's an engineering problem. Okay. Well, thank you very much. Now, maybe there's one more person here who has been in. I think he might have something, but he doesn't have an unmuted mic, nor does he have a camera which is operating at the moment. It's Cornelis. I think he might be there. If you are in the background and you want to, yeah, he is. He always comes in fairly quickly when. So the only thing is your mic is muted, actually, Cornelis. If I bring you, yeah, okay, you're fine now. So do you have any?
I'm here, but I don't have too much to say on the subject. I haven't studied that much, but I look at binding energy. I'm looking at binding energy more as an interaction between waves and that. And in my simplest model, it's kind of like combining two bubbles on the surface of water. The tension when you combine two bubbles, the tension, which would be the energy, is reduced when you take those two bubbles and combine them, and they will attract each other because of the surface tension. But the surface tension is reduced when you combine them, and the excess energy is then distributed throughout the rest of the surface. And I equate that to binding energy and mass defect, basically. Other than that, I really don't have too much to say about the atomic structure. I'm more in favor of a circulating electromagnetic wave, a captured wave pattern of the atoms, rather than a simple ball put together. It kind of reminded me somewhat of Franklin Who's Lego model of the atom.
Right.
So I really don't have too much to say about it. And I'm in kind of a noisy environment. I'm donating blood right now, so that's about it. Thank you. I appreciate the talk.
Well, thank you very much. I hope your blood pressure hasn't gone up just momentarily. I see you have a sleeve there. No, thank you very much. You're always a good man for conceptions, I think.
Yeah. Well, it was a good way to pass the time anyway. I've got another half hour to go. So thank you.
Okay. Well, thank you very much. Unless you have anything specific to say about that, Edo, we'll
I like what he pointed out with the two spheres through the surface pressure. I think he used the term there, how that might explain it. Now that might be the principal effect that's going on there on that very tiny small level, of course. So he may be onto that, onto something there. The problem with fundamental physics, if we go so deep into so much detail and try to understand concepts and terms, often are become blurry as well, or it becomes almost impossible to use words to convey certain things. It really is at the limit of understanding at the moment, at least for me personally. On the other hand, by keeping things as simple as possible, you can, I think achieve a whole lot more. That's what I started out with, and I like where it's going so far. So thank you for the comments there.
Okay, well, thank you very much. I mean, your talk, I'm not surprised at this at all. Your talk has certainly given rise to a lot of comments and consideration, which no doubt will not merely be immediate, but will be when people get to think about this. And I always remind people, and you know this well, Edo, that this is recorded. The recording will be available immediately after we end the stream shortly. So, what has Jim Morrison said? He's got another point. Okay, you're welcome to it. We have a few minutes left, although we're running out of time. Jim has come back and he said he missed how you explained how two protons and one electron can stay together, Edo.
Simple attraction of the Coulomb forces calculus.
Okay.
So ask the AI to do that. You have to use work on your questioning, I guess. But ask the AI if that would work. We're working on a paper actually. Thank you for that question. We're working on a paper actually. Me and two compatriots in the cold fusion community, right? With Mizuno, if anybody knows that community a little bit. Mizuno is a well-known name there. He's there too. And with an entrepreneur, Daniel Grunberg, and the three of us are preparing a paper that points out exactly that, meaning how does it work, whereby you have two protons being held together by one electron, and then you have all the calculations, worked out in that paper. It's a short paper with just that one thing. So it works very neatly, I would argue, no matter what you do. And it's simply the concept of, a negative charge, two positive charges, and how that would stay together. And yes, that does stay together.
Oh, okay. I was just reading.
It doesn't falsify the structured atom model concepts. I think that's the proper way of saying it. So
I was just reading these new comments from Green Science. I put them up by accident, but it doesn't matter. They're just a bit complex, how neutral medicine. You got another one here.
Oh, right. There are multiple.
Best model
Yes,
spinning trap comparisons, blah, 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 and deuterium binding energy.
Yeah.
No, actually, I happened to be myself at a Christmas dinner the other evening, and there was a gentleman who's interested in science. He loves talking to me about science, but he's not a scientist by any means. And he said to me, "Oh, is the electromagnetic force the strong force?" So I said, "No, the electromagnetic force is, say, 10 to the 19 times the value of gravitational force, a very weak force, but the strong force is what is, according to the mainstream anyway. I wasn't thinking of your model, is what holds atoms together by quarks and so on. But it's a very strong force, the Coulomb force, indeed.
It is enough, and that is, and anybody can check it for themselves. I'm sure you can. And use of AI, we can do lots of stuff. You don't have to do the nasty formulas, right?
Yeah.
And
so
one electron in between, and in the distance to both the positive charges on opposite sides, is half an r of the r between the distance between the two proton centers. So the roughly. I think exactly in this system, but the attracting force is double that of the repelling force. So there's not an issue there, not in that sense.
You don't even have to plug in the numbers. You're just getting the ratios, I suppose.
Yeah, you can do it that way already. And if you plug in the numbers, ratio works. It's actually there. It's logical. And like I said, it's a very simple paper that's put together and it's coming out soon. And anybody can reproduce this, no problem.
Okay. Well, it's coming to the time where if there is one more question or so, we could perhaps deal with it, or even somebody, if he wants to put up his hand in the green room. But I'd like to give you a few minutes, maybe 5 minutes or something, to summarize the talk at the end. So in order for me to give you that and not to end after the 2 hours have expired, I think we'd probably have to start drawing the talk to an end. I'm just checking nobody else wants to come back. But anyway, look, this isn't the end of it. It is possible to, and in fact, you are invited to consider these points further and to communicate with Edo directly, or perhaps through us. That's quite all right. Okay. Well, so what I'll do, I have a few comments to make later on before we finish the stream, but I think maybe before I make any of those comments, which are basically on the paper today, and expressing our great appreciation for the trouble Edo has taken to present this in a very, very clear way. Actually, it's quite a complex subject, and he's got new ideas. But I'm going to go down and give Edo as long as he wants. If a minute will suffice, or if he wants to speak for 5 minutes, 10 minutes probably would be too much. But we can afford a few minutes, just maybe to give us a further take. I hope it's been of benefit to you, all these questions, from people who haven't been as intensely involved in this subject as you have, obviously. But in the way, and okay. Okay, just saw the news shop. So, in the light of our discussions today, in the light of maybe presentations, considering what people have said in the green room, maybe a few humble comments I've made, you might like to summarize and tell us where things are and where you hope things will go in the future. And then I'll come back and formally close the meeting. So I'm going to give you the entire floor again for as long as you want, a few minutes, Edo.
Okay, free writing. I would like to say that what I presented today may sound very definitive, like this is the end all and be all. I don't think that is true, however. The way I look at this research myself is that it is research. It is a work in progress. It is meant to do away with a lot of things that I consider unnecessary. Unnecessary, for example, and I understand that there are many people out there that will feel very differently, but allow me to maybe disagree, maybe not. I feel things and concepts like neutrinos, antimatter, wormholes, neutron stars, etc. They are concepts that were invented, postulated, logically constructed, perhaps for very good reasons, but in the end they are useless. What I find out through my own travel and quest in this stuff is that it is an amazing story. There's so much to discover still. We truly do not understand much at all yet. And I was raised and educated in a way that you go away with the feeling, we figured out pretty much everything already, even the beginning of the universe, we got it down. And then when you start thinking, and I think this is crucial too. So this is a journey for me. It's a quest. It's a beautiful quest because, thankfully they didn't do it. Now I get to do it, and it's pretty awesome. But we need to do some homework again. We need to do away with all the answers that we already know. On the Sunday session, there was a nice session about grammar, logic, and rhetoric. At least that's how I like to point it out. Proper thinking. Those are the classical teachings, right? The trivium and the quadrivium. So you have to start with the observation. And from the observations, you create the logic. And it automatically flows that way. And then when you have a whole bunch of logics together, you have the rhetoric. You can do a presentation then, right? You have something. You have a model, a theory, a whatever, an understanding at the very least. If we start out with the rhetoric, meaning the universe started out with a big bang and da-da-da-da-da-da-da, we start with knowing the answer. And that is why I said this model only worked because I did away with all those concepts. any concept that you bring up is also contaminating the mind. So the moment our collective minds were affected or infected with the concept of antimatter, anybody jumped on the wagon. I find that I can do all the calculations, all the explanations in the nuclear physics, as I tried to show today, in a nutshell at the very least. There is no need for neutrino. There is no need for antimatter. There is no need for it at all. And so cosmology is affected very much through the field of nuclear physics. I think those two are completely connected, the largest and the smallest level, if you will. Because proton, that's making a deuteron. That's somehow how the universe has to function, right? The lighter elements. The mainstream gives answers about neutrons, how they were there in the beginning. Yet beta plus, beta minus changes protons and neutrons all the time. The mainstream isn't consistent. And that is a shame. I think the dissident group I'm getting to know here actually holds themselves to a higher standard than the mainstream does at the moment, despite the beautiful words. I want to thank everybody for this opportunity. If I said something that you do not agree with, you have every right to do so. Please just don't vent anger or anything. We need to be polite to each other, But disagree, yes, by all means. Know it better, show me how it's better, right? I will learn, and I will change my perspective. I think this is the way to go, and I think we have some amazing discoveries to make still in our lifetime. And I want to conclude with that. I don't know what to say anymore, Ian. I thank you very much for this.
I think really the words are for us now, Edo. Thank you very much for that, and actually for the summary as well. So it's my pleasant duty, actually. Well, it's not always pleasant to finish the conference, but it's my pleasant duty to have to say a few words. First of all, our thanks are actually due to Edo for his very, very logical presentation of this. So you can see he's a very, he's following these Grecian principles of logic, speaking language correctly. His descriptions are very, very accurate. And, what he just said now, not getting emotional and being willing to change one's viewpoint in the light of what somebody else says and so on. Being collegiate, not getting annoyed with each other, but harboring the possibility of disagreement, which is actually fine. I think all these things are valued. And one of the, I think he's hinted at this maybe in just his closing remarks. One of the questions that it poses itself to themselves, to me, in considering the orthodox science, is that they're saying the macroscopic doesn't talk to the microscopic. They know themselves that there's something fundamentally wrong with their cosmological theories vis-a-vis their atomic theories and so on. And I think Edo's endeavors now are a commencement. They're not the end, but they're a commencement of maybe resolving some of those issues instead of, blindly sticking to our orthodoxy because it's based on the authority of the last 100 years or whatever. So thank you very, very much for getting in touch with us, and we hope to have you back again. I know you are participating in the other sessions as well, and we'll see you at those as well. So again, I'd like to thank all the participants throughout 2025. People who have participated through Facebook and YouTube, and also people who've gone to the trouble of entering the green room and engaging in a more detailed discussion. This will, I think, be the last session of 2025 that I shall host, actually. I'm planning to resume very early in the new year. But so therefore, I'd like to wish all our participants, and indeed our speakers, including Edo, a very Merry Christmas and a Happy New Year. Now, I had been a little worried towards the end of this year that we were running out of offers of speakers, but I'm glad to report that we now have a schedule which I think is filled until the end of February. But if any of you or any people that you know who've been working in areas that would lend themselves to giving a lecture, perhaps maybe from March onwards, we'd be delighted to hear from them. And again, I just repeat what I said to Edo, that this gentleman in Belarus who perhaps ran foul of the Orthodox authorities there, if you'd maybe get him to contact us, we'd be very happy to have a talk from a person such as that. Yeah. So okay, it's conversation on ether. That's another subject. So once again, I shall be leaving you. We'll probably have the first conference, which I shall be moderating on a Saturday afternoon, very early January. And thank you so much, Edo, for your very comprehensive and clear presentation. We wish you the best of luck in your further researches. And once again, everybody, thank you for your participation. I'm going to end the stream now, and I wish you all the best for the season. Thank you.